So the first type of equation that we're going to want to practice writing and balancing is known as a combustion reaction. Combustion means to burn. And for this class, you're typically going to be given some kind of hydrocarbon fuel. Your hydrocarbon fuels are compounds that contain carbon, hydrogen, and potentially oxygen. And it pretty much encompasses most of the things that you think about burning. So propane gas, paper, sugar, even trees and other organic material, carbon, hydrogen, and oxygen are going to be their primary components. So hydrocarbon fuel, and then in order to have that fire, you're going to need oxygen. So oxygen gas on the reactant side, it's an extremely predictable pattern. On the product side, you're always going to have carbon dioxide and water. And both of those things are also going to be in gaseous form. Sometimes students ask me, well, why is the water gaseous? I thought water was a liquid typically at room temperature. But remember, you're talking about a fire. So there's a lot of heat involved, and the water that comes off of the fire at first is going to be a gas until it has a chance to condense when the temperature cools down a little bit. In terms of balancing the equations, we can only add subscripts out front. So right in front of the hydrocarbon fuel, in front of the oxygen gas, and the carbon dioxide and water on the product side. You can't manipulate or change any of the subscripts in our formulas. Those have to remain the same when you're going through the process of balancing. In our first problem here, we're asked to come up with a reaction that describes the combustion of ethanol. Ethanol is drinking alcohol. So the first thing I'm going to do, this is one way to write ethanol. It's a very descriptive way, and it helps us envision exactly how all of the atoms in that molecule are connected. However, it doesn't really help me in terms of balancing. I'm going to condense that formula down, and I'm going to write it as C2H6O instead. And the ethanol is a liquid. And since it's a combustion reaction, we're going to need oxygen gas. And we're going to produce carbon dioxide and gaseous water. All right, so coming up with this part of the combustion reaction shouldn't be too painful because, as I mentioned earlier, the pattern is super predictable. I think the frustrating part with combustion reactions is balancing them. These are the hardest types of reactions to balance. Let me show you how I approach it. I always start with carbon. And so since I have 2 carbons over here, I'm going to throw a 2 in front of the carbon dioxide. And then I have 6 hydrogens, so I'll put a 3 in front of the water. 3 times 2, that's going to give me 6 hydrogens on the reactant side. I always leave the oxygen till the end. This side is more locked in place. Where I have my flexibility is with the oxygen gas. So let me count up what's going on with the oxygens on the product side, and then I can come back and fix this coefficient. So I have 2 times 2. We have 4 oxygens from the carbon dioxide and 3 oxygens from the water for a total of 7 oxygens on that side. Here, even though we didn't explicitly put it, there's a coefficient of 1. You don't need to write the ones. They're understood. But out front here, I have 1 oxygen. And so in order to get the 2 sides to both have 7 oxygens, I need 6 more oxygens in this position here. So if I put a 3 in front of the diatomic oxygen, then the equation is balanced. Methane gas is CH4 And then since this is a combustion reaction, we need oxygen, carbon dioxide, and water. In terms of balancing this equation, I'm going to use the same approach that I did in the previous problem. Start with carbon. One carbon over here. So I'm going to write it just so I remember. I'm going to put one in front of the carbon dioxide, and that'll give me one carbon over there. 4 hydrogens. So I'm going to put a 2 in front of the water. 2 times 2, that gives me the 4 hydrogens. For oxygens now, I have 1 times 2, 2 oxygens associated with carbon dioxide, and 2 times 1, 2 oxygens associated with the water. There's going to be 4 oxygens on this side. I come back over here, and there's no oxygens associated with the methane. So by putting a 2 in front of the oxygen gas, 2 times 2, that's going to give me the 4 oxygens I need to balance the equation. In problem number 3, we're asked to write a reaction describing the combustion of glucose. So I already set that up, and now I just have to balance it. So 6 carbons over here, so I'll put a 6 in front of the carbon dioxide. I have 12 hydrogens. So I'm going to cut that number in half and put a 6 in front of the water. Now I need to count up the oxygens on the product side. 6 times 2, that's 12 oxygens. 6 times 1, that's 6 more oxygens. We have 18 oxygens over here. In the glucose, we have 6 oxygens. And so in order to get up to 18, I need 12 more oxygens. That means that I need to put a 6 in front of the oxygen gas. In our last problem, we're asked to come up with a reaction to describe the combustion of liquid propanol. The first thing I'm going to do to make the task a little bit easier for me is take this formula and put it in its condensed form. In order to do that, I need to distribute this 2 to both the carbon and the hydrogen. That gives me 3 carbons, 3 hydrogens, plus 4 hydrogens. 2 times 2 is 4, plus another hydrogen over there. So altogether 8 hydrogens and 1 oxygen. The rest of the format of the equation, the reaction here, is going to be the same. The oxygen gas, carbon dioxide, and water. Alrighty, so I have 3 carbons over here. I'll put a 3 out front here. 8 hydrogens, split that number in half. 4 times 2 is 8. Carbon and hydrogen are fixed. Let's look at the oxygen situation. 3 times 2, over here I have 6 oxygens. 4 times 1, that's 4 oxygens. This is a total of 10 oxygens. Here I have 1 oxygen. I'm going to need 9 more oxygens to get up to the 10. But looking at this, we can't get there, right? This is O2, and there's not going to be a coefficient unless you want to use a fraction. I'm not a big fan of the fractions. So there's not a coefficient that we can use to change that to a 9. In my head, I don't know why, I call this an even-odd problem. We're looking for an odd number of oxygens, and we have this diatomic or even compound. So in order to fix an even-odd problem, you're going to want to double everything else. So out in front of the propanol, I'm going to put a 2. Remember, there was a 1 there, but that 1 was understood. I'm going to 2 there. Cross out this 3. I'm going to double it to a 6. And then I'm going to cross out this 4 and double it to an 8. Let's see how that works out. So now we have 2 times 3. We've got 6 carbons over here. 6 carbons with the carbon dioxide. 16 hydrogens with the water. 2 times 8. 16 hydrogens with the propanol. Now let's fix the oxygens. So 6 times 2, we're going to have 12 oxygens. Getting kind of messy. It always gets messy. Use scrap paper, use pencil. 8 times 1, 8 oxygens. So now I have 12 plus 8. On this side, I have 20 oxygens. Over here with the propanol, now I have 2 oxygens associated with the propanol. I need to get it up to 20, so I need 18 more oxygens. So by doubling everything, now I have an even number here and an even number here, and I can fix that relatively easily with a whole number coefficient.